between proof complexity and algebraic complexity. And our first talk will be by Iddo, giving us a
Thank you, Yes, so thank you everyone for coming this morning. I think I have the microphone on, so it's all good. So I'm going to give a kind of a survey of the state of the art of lower bounds on proof complexity via algebraic circuit complexity. Not all of it are going to be just the lower bounds, but I'm going to show you something quite interesting, I think, or maybe even very interesting. Let's discuss this at the end, is that what happens in recent years is that a lot of open problems that are basically open, major open problems in proof complexity or boolean proof complexity, and proof complexity from the perspective of Frege proof system, logical proof systems, are actually solved in the algebraic world. And I'll show you what I mean. And let's see precisely what are these results and what do they mean for proof complexity, and discuss a bit of open problems in the frontiers of this approach, and also how to actually leverage this approach to the traditional open problems of proof complexity. These are open problems. So this is going to connect both proof complexity, people interested in mostly strong proof system, Frege, AC0, Frege, and so forth, but also it's going to be tailored for people in algebraic complexity. There are several here, and I'll give some detail of some of the results in algebraic complexity. And so let me repeat what we've usually doing. In proof complexity, we are doing, oh, the clicker is here. So what we are doing in proof complexity, for most part, is the following simple question. Given a proof system P, are there hard instances? Now, hard instances, so I'm going to do it quickly. This means that these are tautologies such that P, the proof system, doesn't have a short, this is a short proof, does not have a short proof of this tautology tau, which simply means that does not exist a P proof of tau of size polynomial in the size of the formula, right? That's major, that's the main question of proof complexity, right? And Cook's program, which is in some sense a program, Jan Frege told us about this program and cast doubt about the fact that it was a program. I think it is in some sense still undertones all research in proof complexity, so it is a program. It's just that practically in science, or in this branch of science, people do not formally say this is a program. So nobody is going to say this is a program, but definitely this undertones, and this is the ideal behind proof complexity. So, and this is the following: if for all proof system P there are hard instances, then NP is unequal to co-NP, and also P is unequal to NP. So in some limit ideal case, it means that proof complexity is taking us step by step towards P versus NP in this sense. Right. So let's see what are the major open problems in proof complexity, or some of them. So hard instances for strong proof systems. So we know these classical result by Iddo, and then Impagliazzo, and Frege, Woods, and Podlag for AC0 Frege lower bound. So yeah, you can ask questions all the basic definitions. So are there hard instances for strong proof system beyond this? So this is one of the major open problems, and it is open. Now, we sometimes want also to ask the following. Okay, we cannot prove these hard instances for proof complexity exist, but maybe conditional proof complexity lower bounds exist. Maybe we can prove for strong proof systems. For instance, computational lower bound imply some extended Frege, I denoted EF, lower bounds. Computational here means something different than NP is unequal to co-NP, which is almost immediately this implication. It means that EF has hard instances. This is the question. Conditional lower bounds. And something slightly more specific than this, we want to ask whether we have a very tight connection between circuit complexity and proof system. So do we have this kind of result? Circuit lower bounds implies strong proof system lower bounds. Right. Also mostly open. There are a lot of results here in the regime of weak proof systems that I haven't specified precisely. Maybe the most prominent is the interpolation technique that we've already heard of. And that's why I put here this points known for proof system with monotone feasible interpolation, where we use monotone circuit lower bound to get proof system lower bounds by reduction from a small proof to a small monotone circuit. And because we already know monotone circuit lower bounds by Rasborov and etc., we get lower bounds. But these are in the regime of the weak proof system. There is this point about non-commutative formulas, lower bounds for, and this is the point, it's a circuit lower bound, but it's for a family of, in some sense, semi-defined polynomials would imply already strong proof system lower bounds. This is also in this algebraic approach. It's a result with Li and Wang, but I'm not going to cover this one. So this shows something about this circuit lower bound imply proofs, but it's not, I wouldn't say it's direct as we want. It's not a precise lower bound. It's a lower bound on some family.
About what is semi-defined polynomial?
Yeah, the semi-definedness means simply that it's a family that that precisely define the so-called IPS certificate, the non-commutative. So basically, it's a sorry. Yes, but the IPS lower bound is a polynomial, and we can characterize this polynomial. We don't know precisely which polynomial. We know some family of polynomials that produce this IPS certificate. So it's kind of a game. Yeah, I'm not going to touch this result. Conversely, does strong proof complexity lower bounds imply computational lower bounds? So, for instance, does EF lower bounds, standard Frege, implies such does not have small circuits, right? So in some sense, Cook's program realized already with, this is how I write with, if you see, with extended Frege. So Jan Pich talked about this yesterday, and basically his work with Rahul tried to attack this point. The EF lower bound, whether EF lower bounds would imply computation complexity lower bounds. These and Jan's and Rahul's result were conditioned. Right, of course, in the weak regime, weak proof system regime, some results for resolution to monotone circuits are known. I think one paper is Gar, Gus, Kamath, and Sokolov. You have this kind of ideas, again, in the weak regime of proof systems. There might be other. I mean, it's a well thought out question, so there might be other papers here. So I'm going to produce a solution now, of course, in brackets. And the solution to all these major problems can be done as follows. We can expand the language of unsatisfiable formulas. So if we expand the language to still a natural language, a co-NP language, in the following sense. And this is a traditional thing. It's a natural expansion. It's not something unique. It's the following. So let's assume we have this proof systems, usual one, unsatisfiable formulas with these logical gates and or not, right? CNFs and so forth. And we have the usual proof system, resolution, Frege, and so forth for propositional tautologies in this language. We expand it a bit to include also sets of polynomial equations over some field. You choose some fixed field, finite field, with no 0-1 solutions. So it's important that there's no 0-1 solutions. So it's still propositional. So, and this was, for instance, an example, just a linear, unsatisfiable equation over large enough field. So, you see, this is the language that we use in algebraic proof complexity or algebraic proof systems, the traditional one, PCA, polynomial calculus, Nullstellensatz, and so forth. And indeed, the original results were on this kind of algebraic instances, not CNF instances, original principle, and so forth. So this is the language we work with, not just CNFs or boolean formulas, but sets of polynomial equations over a field with no 0-1 solutions. And it's still a co-NP set because of the 0-1 solution. So we can check if it's satisfied. We check if a solution is weakness is satisfied. Right. So this is a very natural extension. It can be even considered not as natural as CNF. And in this regime, we actually, when proof systems are proof for this language, expanded language, I'm going to show you that a lot of the major open problems are actually solved to a certain degree of satisfaction. Right, and these are the proof system that are interested in this regime: polynomial calculus with resolution, Nullstellensatz, and what I'm going to discuss today mostly is IPS, ideal proof system, which we have to define. So here is a sketch of the proof system map. We've seen it in this is slightly not all of the proof systems are there because I want to restrict our interest not to semi-algebraic proof system, just to the algebraic and propositional. So here are a system for propositional logic, resolution, constant depth Frege, extended Frege, and this means this is stronger than this one, this error. And so these are the propositional logic, goes from weak, strong, and well, I said here it's very strong. And here in this more yellow region, it's a proof system for logic, but also for algebraic, for systems of equations over field with 0-1 variables, right? So this is not Nullstellensatz, polynomial calculus, and IPS. Now, as I said, we should see that the open problems mentioned before have solution for IPS. I'm going to define it where the hard instances are non-Boolean.
One value.
It is 0 for one value, but for instance, it's not going to be a CNF or a formula. It's going to be a function maybe, or a polynomial or a linear form, where when you plug in 0, 1, you still get many values. 1, 2, 3, 4. You cannot do it in the Boolean setting. And that's the obstacle, of course, to go from this setting to the CNF setting. So here is ideal proof system introduced by Groucho and Pitassi. This is the journal version. So basically, this idea of ideal proof system was circulating. It mostly initiated, I would say, in '96 by Tony Spitzer. These ideas of thinking about the complexity of proof system via algebraic circuit size instead of Boolean circuit size. But they had some crucial idea here that I will show you that made it possible to do it more elegantly and have some nice results. So here is the ideal proof system. It's a very strong one, a proof system for the language that we are interested in. And these polynomials be multivariate with, let's say, n variables, x1 to xn, f1 to fm, in this polynomial ring over field. It's not important now which one, but we have to fix it over field f with no 0-1 solution. So 0-1 solutions means that this means that there is an equation here with 0. So all of these need to be 0. So there is no way to satisfy all of these equations with the 0. So a refutation is the following term. It's just a sum, a polynomial sum of the axioms. So these are the axioms, f1 to fm. They are unsatisfiable over 0, 1. So I will also add these, what I call Boolean axioms, x1 squared minus x1, also over 0, 1. It means that every solution every solution should satisfy this one. And I'm going to have this sum. So this sum says, for some polynomials, I just choose the polynomial g1 to gm, I multiply them by the axioms, and then I choose also other polynomials, h1 to hn, and multiply these Boolean axioms, right? So you see every term here, every summand is a multiplication of one axiom and some arbitrary polynomial that I choose for my proof. And I'm going to say it is 1. Namely, 1 here is polynomial identity. So it's important. It's not 1 as a function. It actually means that this polynomial, when you multiply out all the brackets and so forth and sum everything, all the monomials are 0 except the constant monomial, and it is 1. So we discussed this a bit, I think, in Yuval talk. And by the way, how do you check this? Yuval also explained to us, but this is commutative. So this is simply this proof system cannot be checked, is not known to be checkable in proofs are not known to be checkable in polynomial time, deterministic. You need the probability, so you do it with Schwarz. So it's co-RP. I wrote it on the next slide. It's not important for us. Right, this is a bit small font, but the soundness is easy, right? This sound, because if you have a proof, then it must be unsatisfiable. Otherwise, you wouldn't get here 1. And completeness, well, 2 proofs are possible here, or maybe more. One is Hilbert-Nusssteinersatz. This is how it was conceived in the 90s by Pitassi, Impagliazzo, the Nullstellensatz. Impagliazzo, Krajcik, Budlak in 94, 90 something. So this is the Hilbert Nullstellensatz, but we don't need this fancy algebraic geometry. We can just have a constructive argument because we have these Boolean axioms. We can go by induction on n. That's complete. It's not necessary for us. So IPS, ideal proof system. Oh, so what did I say here? Yeah. Well, I still didn't define the ideal proof system. I defined this term. This is the Nullstellensatz. And now I'm going to discuss the ideal proof system. Now, with some caveat, I'm going to use what is called actually linear IPS, because here I'm not going to have these multiply themselves. It's not the constraint. So the same thing, FIs are a set of polynomials, which is no solution. And the refutation is this. And now, so I took these and I put a box, a red box here. And this is the idea of Groucho-Pitassi. We take these axioms and change them into y's and z's, variables, new variables. That's the main idea. Instead of thinking of this as a term, now we're going to plug in these variables instead of these guys. And what do we get? We get a polynomial, a single polynomial, such that this is what is happening. I don't know if it's it might be a bit small. So now, so so you see this, and now you get this polynomial. We get that this and these are the variables that I substituted here. And so this is actually now a polynomial, a single polynomial. It's not a family of polynomials anymore. It's a single polynomial. Each proof is a single polynomial in these very formal variables, x, y, and z. And these are the placeholder variables, because then we plug in the axioms and we get the following. So let's call this polynomial C with the displayed variable x, y, and z. And when we plug in 0 for the y's and z, of course, we get 0 because of this, right? Because this is how it is defined, which means that we work in the ideal generated by the axioms, basically. And the second condition is then when we plug in the axioms, it is 1.
X squared minus x. Instead of h.
Yeah.
Yes, sorry.
So in the linear case, it's not equivalent to requiring the g's to be given by circuits.
So you say that, okay, let's just say this is a typo, so it should be these Boolean axioms, sorry. And Yuval asked whether, because I said that these cannot multiply themselves, so I said it's linear IPS, and Yuval claims that it is identical to the general case.
No, I'm saying that you can ask instead for the g's and h's, instead of being given as list of coefficients, is being given by circuits. Is this the same system?
No, it's not the same circuit. I still didn't finish my definition. The system, if it's given by list of
By algebraic circuits.
sorry. Yes, it's going to be algebraic circuit. Let me just define. So again, this is polynomial densities. And yeah, maybe I should have.
So I guess the question is like, are there restrictions on what how C can be represented?
Yeah. And this is the restriction. IPS is measured by, so for now it's just a C, but IPS is measured by size of algebraic circuits computed. Yes, I didn't say. So the IP, this is the size that I'm going to measure, but I want to in somehow disassociate it from the definition because I can say this is a proof, C is a proof, it's just a polynomial, single polynomial, and now I'm going to change, it's going to be a modular definition, I'm just going to change the size measure. So I'm going to say the size of the IPS is measured by algebraic circuit, but now I'm going to say maybe from some restricted circuit, plus constant depth circuit, so forth. So that's why I said it like this, but Johan is right. So IPS is measured by size of algebraic circuit, and because here we are going to have a lot of talks about algebraic complexity, so I'm going to briefly define this. Algebraic circuits is just a directed acyclic graph with edges directed from leaves to root, such that we have internal nodes plus and times, and leaves are field element or input variables. Something like this. Each node computes the corresponding addition or times of the two polynomial in its tables.
So you say algebraic circuits will be GIs and HIs, but the way you define it, that's just C.
Yeah, but it's equivalent.
It simultaneously computes all the.
Yeah, but that maybe that tree explicitly said that if you look at Lufthansa's and you compute the total size of the G's and H's. So that's the same thing.
Yeah, correct. So you're right. I didn't say this explicitly. So yeah, the point is that I wanted to circumvent this and just show people this, but actually let's forget about this fancy looking definition and just concentrate on this. So, because this is like the usual Null standards, but indeed in the general circuit case, it's identical. But let's just talk about this one because this will be helpful in our proofs. So I'm just going to sum the sizes of these H and G. And this is algebraic circuit, size is number of nodes.
Size for Lufthansa.
Sorry?
How do we usually measure size for Lufthansa?
Just sparsity, number of monomials. Sigma pi. So IPS refutation, we discussed this, and size, and that's what I wanted to say. It's just the size of this GIs and HIs. Again, I'm forgetting about this CI, the C. So. And this is the size. Now let's see what we have. So as I claimed before, open problems in the Boolean proof complexity or Frege-style proofs actually have solutions in this algebraic world when we expand the language to non-CNF instances. So, open, yeah, so let's see this. This is open in the Boolean world, what I've discussed before. Conditional proof complexity low bounds against strong proof systems. For instance, some computational low bound, different than co-NP, NP, implies some strong proof system, extended Frege low bounds. Open here. And this is in some sense solved by this result. So this was the result with Alexeyev, Grigoriev, and Hirsch. So it shows the following. If we take for I think I wrote it correctly here. It's quite small. If we assume this hypothesis from algebraic complexity, that there are no polylogarithmic size algebraic circuits computing multiplication of factorials. And here it's algebraic circuits only with constants on the leaves. And the constants are 1, 0, and -1. So you build the constants on this number, you want to build it with plus and times, and at the end, it evaluates to this number, multiplication of factorial. And if we assume that for these kind of numbers, we don't have a small size algebraic circuit in this sense, and this is the Schub-Smale hypothesis, it's not proven, it's open. If we assume this, then we actually get a solution to this problem. No polynomial size, IPS, here it's over Q, refutation of this simple instance. This instance is what we call the binary value principle. It just, these are 0, 1 variables, and this gives us and this is the bits of a number, and this is the value of the bit string of the binary number. And we say here it is unequal to -1. It's equal to -1, which is impossible because these are zeros. So you see that this is already some advancement. Of course, well, I will talk about a bit about the caveats here, about the coefficients here are big. So let's go for the next one. So open problem in the Boolean world, circuit lower bound implies some strong proof system lower bound. So actually we know this in some sense. There's also a caveat here. VP is unequal to VNP, which is a computational lower bound saying that the permanent polynomial doesn't have polynomial size circuits here, it's over finite fields. If this is true, then we know that there are no polynomial size IPS refutations of a certain specific CNF. So we get this, the thing that we want in the Boolean case, that strong computational lower bounds or complexity class separation implies strong proof complexity lower bounds. This is a result with Santanam. This is of a finite field. And the caveat here is that this is true. No polynomial size refutation of this CNF phi, only that we are not sure that this phi is actually unsatisfying. So we know that it doesn't have short proofs, but it might be just do not have proof. But if it has the proof or refutation, it's not short.
Well, I mean, it's clearly if if VP is equal to VNP, it clearly can't have a proof, right? So
No, that's not the point. But
so is it in a stronger sense that you don't know phi?
Oh, yeah, it might be that VP is unequal to VNP. This is correct, but we just have short proof of it.
Right, but yeah, just the statement that you don't know that it's anyway. Yeah, okay. Yeah.
So, so this is phi. So this was kind of a diagonalization argument. So, but this is a CNF, which is nice.
I'm sorry, but the system cannot prove that the sum of, like these non-negative numbers is non-negative, but somehow, why, so what are the odds that it could prove something like P is not equal? Right. You understand it, right? I mean, but, why would we be looking at sentences like, it cannot prove that P is not equal to NP if it can't prove that? I don't know if that's a fair question, but.
Yeah, so the answer is yeah. So I would say it's not a correct question in the following sense. If indeed from this we would already know that this CNF is unprovable, then we would get then we would get also, and this is a CNF, what I said before, then we would get stronger proof complexity.
It simulates other proof systems, so IPS simulates other proof systems. So
yes, IPS simulates other extended Frege, depending on the degree of Frege. So this is a non-CNF, but for CNFs, we don't know how this.
Oh, I see. That's a CNF. All right, I understand.
So, yeah, but that's a reasonable question, I guess.
That's the Schwarzschild process imply that
Does the Schultz-Smale hypothesis imply VP unequal to VNP? I think it does, yes. It's a result by also Burgisser, it depends on, and also the originals, yes. Yes, it's written on the paper. Oh, and of course, now we flip the direction and we have this open problem in the Boolean world. Does strong proof complexity lower bounds imply computational lower bounds? If lower bounds imply, for instance, maybe sub is not in P/poly. So, and this is in the algebraic world, it's actually being settled in the following sense. If there is no polynomial IPS refutation of some CNF phi, doesn't matter which one, then Grocho-Pitassi original work showed that,
Yeah, it should be answered.
That's satisfiable CNF.
yes, of some unsatisfiable CNF, of course.
What's the sound?
Yeah, it's logically it's correct. Yes. Of some CNF. No, yes, right. So this of unsatisfiable, of course, sorry. Then VP is unequal to VNP. Yes, excellent. Obviously. VP is unequal to VNP.
Reduction at all.
And this was done by Grocho-Pitassi. Yeah, basically the argument was a truth table argument showing the following. Every CNF has a truth table, simple IPS refutation going over all the assignment more or less, like Yuval did, summing up everything. And this certificate is exponential size, but it's actually computable in VNP, right? So because every CNF has a VNP IPS certificate, if you have a lower bound, you have separated VNP from VP for CNF, not for other. But I don't prove this. Now we go to the more, let's say, algebraic / combinatorial meat. This unconditional proof complexity lower bound for strong proof system. So we've seen this open problems in the Boolean world, which are in some structural questions about conditional results that are in some sense settled to a certain degree in the algebraic world. And now I'm going to show that hard instances actually exist in this world. Unconditional. So the first one, of course, is, it's not precisely in the IPS, but I should mention this. It's in the proof system that is PC plus some extension variable, sorry, not extension X, sorry. Well, these are axioms also, but extension variables. But let's call it like this, P plus EA. So PC plus EA plus extension variables is polynomially equal or stronger than extended Frege. Yeah, that's correct. Because PC with extended variables is already simulates a resolution with extended variables. Equivalent? No.
Oh, depends on the field.
No, it's not. It depends on the language also. This is for CNF, and this is. Oh, I see. For CNF, are they equivalent?
Depending on the field.
Probably, yes, correct. But what is the? Yeah, but what's the degree? Yes, I think it is correct. Yes, it's equivalent. If the field is fine. So. Right, so this is easy, like resolution plus extension variable already simulates extended Frege. So I'm just giving you this because I want to show that it's very strong proof system. Now, Alexeyev in 21 showed basically similar ideas to the work with Alexeyev, Hirsch, and Grigoriev. He showed unconditionally now that if you take this binary value principle, it does not have short proof. Sorry, I shouldn't say this. It might have short proofs. That just the proofs have coefficients which are so big. So when you compute the bit size of it, they become super polynomial.
So why is it thus? I mean, it's two order, right? Right.
Yeah.
No, it's magnitude. Size.
So,
Oh, sorry, the magnitude is, yeah, 2 to the 2. Yeah, sorry.
oh, 2 to the,
You also allow taking square roots.
It's 2 to the 2. Right. So it's a super exponential magnitude. So the size, bit size is super polynomial. Right. And this, I'm not covering this because this was not in the IPS setting. It's also, it's a very strong result, I think, because this is a very strong proof system, a very natural hard instance, and it doesn't have small bit size of proofs. But some unsatisfactory parts are, these are very, it builds on the fact that these are very large coefficients, and also the proof might be short in the number of steps, but just very big to write. The coefficients are very big.
Is this known? But there is a short proof.
Oh. I don't remember. Okay, let's try to see some of this. Let's try to see the template of the lower bound for IPS. So we call IPS refutation is like this, and this is the IPS, and the size is the total circuit size of these GIs and HIs. So now, as I said, we can consider different circuit classes. Read once ADPs, multilinear formulas for those who algebraic complexity, you know these, constant depth circuits, and for each of these circuit classes, we already know unconditional lower bounds for the circuit classes. Now I'm going to use it based on the lower bound template. Well, I'm not going to show all of this, but it is possible to use the reduction from proof complexity lower bound to algebraic complexity lower bound. It is possible to use these circuit lower bounds to lower bound the size of IPS region with these circuit classes.
For each of these cases?
Yes. I want to show the simpler case, read once ABP. So, right. So let's see how we do the template for the lower bound. So take a single, and this is crucial, you need to take a single axiom. A single 0, 1 unsatisfiable axiom, fx equals 0. And then you do the following trick. Let's assume we have a proof. This is a polynomial identity with 1, right? So all the coefficients are cancelled except the constant. So let's assume I have this one, and I have a single axiom, unsatisfiable axiom. This is unsatisfiable over 0, 1. And then I do the following. I know that G times F equals 1 over the Boolean cube. Now it's already not polynomial identity. Now it's a functional identity. I just restricted to 0, 1, and that's why I took out these guys. Right. So it's a functional identity now. Yes, sorry about this. So this is G equals 1 over F. Oh.
wait, so you just shifted up, that basically just accidentally shifted up that G of X equals 1 over F of X.
Yeah, but now, yeah. So I just wanted to say here, this should be this guy. So Fx is unsatisfied equals 0 unsatisfiable. So this is not 0, so this is okay, right? Because this is never 0. Now let's pick some circuit class C. That's the circuit class that we want to work against in the IPS. In this case, it will be read once ABPs. So if no polynomial computing 1 over F over the Boolean cube has small circuit in our class, read once ABPs, for instance, we are done. That's the lower bound. So we made a very simple reduction to a circuit lower bound. It's not algebraic, usual algebraic circuit lower bounds. We need here the functional lower bounds. So we need here, this is a family of polynomials computing, evaluating to this over 0, 1. But it's a family because over non-zero 1 values, they may be different. We don't know how they behave because they are not multi-linear necessary. Okay, so what we've seen now is we reduced C IPS for circuit class C, and we'll take read once ABPs to the problem, prove that no polynomial G such that this over 0, 1 is in class C. And fortunately, we can prove such lower bounds function in the functional approach to algebraic circuits, lower bounds. And then basically we finish.
Will you tell us which function?
Yes. Oh, the function. Right. Yeah, I'll tell you. But the function f, you mean? Yes. So basically, f. Unfortunately, it's only a single one, and it's always going to be, as of now, some kind of subset sum instance with some lifting. Maybe you take a sum of x's equals sum of n x's equals n plus 1. It's unsatisfiable. And then you want to lift it if you want a more complicated circuit classes. So you say xi, yi, or xi, yi, zi, and so forth. That is always like this. Yeah, that's one obstacle to overcome. So here is the simplest example, I think. And this will be more to the algebraic people that know this model. So for them, it's going to be very simple. It's just read once, oblivious algebraic branching programs. This is the circuit class that we can already prove IPS lower bounds, C IPS lower bounds with. So read ones, ROABPs are just these guys. This is just algebraic branching program. We start from a root and we multiply all the paths up to the sink. And here we sum all the paths. And in each path, we have edges, which are polynomials, which are multivariate polynomials, not necessarily multilinear. Univariate polynomials, not necessarily right? So univariate polynomial, and here we have x1, x2 until xn. Each variable is queried once in each layer here. Each layer has only one variable, and it doesn't repeat, and the variable doesn't repeat, and you have an order, so x1 to xn. And that's the model. Now, the width here is the maximal number of nodes in a layer. Let's say that the width of this computational model is this.
So the functions need to be linear, but you're looking at the behavior on the Boolean cube. So isn't it without loss of generality we can linearize?
No, not everything. If it's you might have no, it's not. It's impossible to multilinear.
In this particular case, you can.
In this case. But not all cases. If it's just a formula, how would you multilinearize it?
No. But Russell's talking about this case.
Oh, this case, yes, this one. Yes. I'm not going to show all the details, but yeah. So let's see this quickly. Size of a read once ABP computing G. This is just a general statement for some polynomial. Is bigger, is at least the width of this read once ABP computing G, of course. And this is at least basically Nissan 91, the maximal of the rank of the ith coefficient matrix of G. Something to understand here. So what is the ith coefficient matrix of G? That's the basic primitive for lower bound in algebraic complexity. you think about G as a vector of coefficients, and you put the monomials, right, and you have x1 to xn, and you put the monomial, if you are in the ith coefficient matrix, you put the monomials from variables x1 to xi, all the possible monomials here, and all the possible monomials from x, here should be I plus 1, and for until xn are here. So you partition it in I, and these are variables until I, and this is from I plus 1 to n. And now this is a matrix, and in the mn entry, you simply put the coefficient of this monomial in G. And you have a scalar matrix here. And this is very useful, because if you think about the rank of this matrix, and you take the maximum one over the I, you get that this already, the width is lower bounded by this. It's possible to show, it's not hard. I recommend reading NISTA 91 paper. It's a classic and simple. Now, here is the trick. This will be quite, maybe slightly confusing for those who didn't see these ideas. It's not complicated again. So, the same as before, size of read once ABP computing G is lower bounded by this, and actually this rank of ith coefficient matrix of G is equivalent to the dimension of the, well, I don't include here i's, the dimension of the space of rows as polynomials in this. So let's assume we fixed I. So space of rows as polynomials in this polynomial. So so I think of the polynomials here, I just take a row here. So it's basically a polynomial in this monomial. So you can show this, it's easy, that's equivalent. And basically, well, that's the same as the columns. And this is a trick of, I think, Ramprasad Saptarishi from 2012. You can think about the following, and you can lower bound this by the dimension of evaluation points or evaluation polynomials which are evaluated in some points over the, in our case, it would be the Boolean cube. So you take the Boolean cube for n minus I, so all the polynomials you have in these variables, right? And you plug in 0 ones instead of the xi plus 1 to xn variables. Plug in elements from the Boolean cube, and you get a set of polynomials. And the dimension of the span of this, or the dimension of this set, is going to lower bound this dimension. That's a trick of this result. And it's not hard to see also. Now, this trick is very useful because what we've done here is this is for polynomial. And now we switch to a measure that measures only points on 0, 1. So it's better for us now because we are in the functional frame. So, right, it remains to lower bound for some G equals 1 over F over the Boolean cube. This. So we've reduced the IPS lower bound for read once ABP IPS to this algebraic problem of lower bounding this. And this is quite easy. Well, I cannot cover all of this, but proving this is easy. And let me tell you very briefly the gist. Here is the idea. So proof degree. So we need to prove a slightly better degree than IPS Impagliazzo Kudlak Sagan 99. It's another IPS. So they prove the n over 2 lower bound for degree of PC. We want Nurstein's degree, which is precisely n for these G. So we can do this. So if G is, and this is our hard instance, right? And this is 1 over our hard instance. So if we have G that computes this over 0, 1, we can show that this as a multilinear polynomial is of degree precisely n. That's not complicated to show. And then we're going to lift this degree lower bound in this dimension argument. We're going to show that the dimension of G, when you plug in for the betas, elements from the Boolean cube is, and this is just by definition, because this is G. And because this is when we plug in y's into, which are 0, 1, we're going to eliminate all the y's, and we're going to survive. Only some of the x's are going to survive. And these are some sums, partial sums of the n variables. But we just show that these must have, as multilinear polynomials, maximal degree. So if x1, x2, x3 survive, it must be that the monomial x1 times x2 times x3 is here. And then it's simple to show, and lower terms in some monomial ordering, and you get basically that the dimension of this is 2 to the n. So that was the trick. I did it quite quick. It's not very complicated, but you need to be, for the people in algebraic complexity, I'm sure that they are quite comfortable with this, but for those in proof complexity, they need to just take some time to see how it goes, but it's not complicated.
Oh, just one question. This works for read once ABP, I guess, but does it also work for non-commutative?
No, for non-commutative, you need another lift, degree 3, so x1, x2, x1 times y1 times z. You do something because the degree is different. You have to read forms and all data. Yeah, so here it is. So CIPS lower bounds, read once ADPs, multilinear formulas, as Hamlin asked, slightly differently, and constant depth circuit. So these two classes of lower bound for CIPS, where it was Frege and Iddo. And this is also, of course, using Raz and Razanir-Diov. And this is a new paper by with Govindasamy and Hakoniemi. And we use the Limaya, Srivinasan, and Tavenes lower bound to get constant depth circuit IPS lower bounds, with some caveat that the polynomial IPS is actually multilinear for some technical reasons. Okay, so we didn't get much to the open problems, but the open problem are obvious. How to get this to the CNF regime? Well, nobody knows. Is it possible? We don't know. Okay, for IPS, if we can do CNF low bound for IPS, we get low bound for extended Frege, so it would be quite impressive. But also we get VP, VNP, so it's quite challenging task. But for constant depth IPS, I think there is still hope. We have constant depth IPS lower bounds for big field, large enough field. And I think it may help in this low TC0 Frege lower bound and so forth, or AC0P Frege lower bound, if we get the CNF. And some intermediate problems, of course, take out the single axiom, so have not just single axiom hard, but two axioms. But of course, there are some very trivial two axiom cases which are uninteresting. You have to think carefully, what do you think, what is actually an interesting case of more than one axiom? Finite field case, also important. Everything here was for a large enough case, because we need, for instance, unsatisfiable subset sum. It wouldn't work for finite case. And also because of Fermat-Little theorem, this functional low bound wouldn't work, but that's simply true. So just finish with some polemics. Perhaps we shouldn't really insist on CNF or Boolean hard instances. And I ask you, we have this, the problems are solved. why do you think C and F are more naturally important than these very natural in hard instances? And this was a question that one should ask. Now, some people might say, okay, we already have these results. I think it's by Olaf and authors for TQBF. If we expand the language, then we get this kind of solution to problems in proof complexity. And also, if we have some first order logic, this is the Friedman results. And I think good luck. But these are not co-NP languages. Here we are dealing with the simple. Yes, so that's it.
Yeah. What about semi-algebraic proof systems? Let's say CPS.
Oh, yeah, there's no result in it. That's stronger. Yeah, it's interesting.
Because for some pairs there are some results. So
Some.
something real or not.
Yeah, but not for the strong ones. Yes, for SOS. Yes, I didn't have everything here is algebraic, not semi-algebraic. There's no real part. Yeah.
I was going to ask roughly the same question. Do you consider the semi-algebraic proof systems to be intermediate between where the problems are solved and where they're not?
No, I consider them as the weak regime, but maybe you can correct it.
What is known about optimal proof systems in this setting?
Do you have any suggestion for something that's beyond C and in co-NP and makes sense in the Boolean case?
If it makes sense in the Boolean case, it would mean probably that it would lead to some lower bound in Frege. So I don't see the answer is no, I don't have any idea. It's interesting to see.
So I just have a comment. This is a comment about the.
No, proof system.
No, we don't even have any system even with CFC.
No, because then it will be means that PIT is in If ZFC can p-simulate IPS, I claim that it means that PIT is in NP.
And we have non-uniform PIT.
Correct. Well,
PIP is an NP makes sense. You and Microsoft flash for you or that common request for less technical.